For months, astronomers have been tracking a silent traveler moving through our solar system. An interstellar visitor unlike anything ever observed before. Known as 3I, Atlas, it arrived from the vast depths of interstellar space, traveling for millions of years before finally entering our cosmic neighborhood. Just as scientists believed they were about to say farewell to this mysterious object, something extraordinary happened. As 3I, ATLAS approached its closest point to the Sun, observatories across the world began recording a series of anomalies so unusual that they challenged decades of astronomical knowledge. Its brightness changed unexpectedly, its appearance seemed to evolve, and then it displayed behavior that no known natural object has ever demonstrated. Today, we'll examine what the James Webb Space Telescope, the Hubble Space Telescope, and several leading ground-based observatories actually observed, and why Harvard astrophysicist Avi Loeb believes this object deserves far more attention than a typical interstellar visitor. The story began when Spain's 2-meter twin telescope captured more than 150 detailed images of 3I, ATLAS as it approached solar conjunction, the period when it would pass almost directly behind the Sun from Earth's perspective. Those observations revealed something astonishing. A narrow stream of material appeared to extend toward the Sun instead of away from it. Every comet studied so far releases gas and dust that are pushed outward by sunlight and the solar wind, creating a tail that always points away from the Sun. But this feature appeared to do the exact opposite. It resembled a rare counter-tail, producing an image that immediately caught the attention of astronomers around the world. Follow-up observations from the Hubble Space Telescope and the W.M. Keck Observatory in Hawaii also detected an unusual diffuse glow on the sunward side of the object, prompting scientists to investigate whether unusual viewing geometry, dust dynamics, or another physical process could explain the phenomenon. Researchers quickly proposed several possibilities. Some suggested that the dust particles might possess unusual properties that caused unexpected interactions with solar radiation. Others explored whether the apparent structure resulted from the object's orientation or the complex behavior of dust released at different times. As additional observations arrived, another mystery emerged. The object's estimated mass, brightness, and motion did not fit together as neatly as expected. Measurements suggested that 3I, ATLAS was behaving differently from the icy comets and rocky asteroids normally found within our solar system. Its rotation period also drew attention. Completing one rotation roughly every 16 hours, the object appeared remarkably stable despite its unusual characteristics. Some scientists even considered whether it might contain significant internal cavities rather than being completely solid. Small variations in reflected light hinted that its interior structure could be more complex than initially assumed. Spectroscopic observations added another layer to the mystery. The reflected light indicated relatively high concentrations of nickel and iron compared with typical cometary material, along with traces of carbon-bearing compounds commonly found in interstellar environments. Although none of these findings alone proved anything extraordinary, together they painted the picture of an object unlike any previously studied. The scientific community quickly divided into competing interpretations. Was 3I, ATLAS simply a rare natural object formed under conditions never before encountered? Or could it represent an entirely new class of interstellar visitor? As discussions intensified, Harvard astrophysicist Avi Loeb introduced an idea designed to organize the growing debate. Inspired by the Torino scale, which measures the potential hazard of near-Earth asteroids, Loeb proposed an object of extraterrestrial probability framework, or OEP scale. The concept attempts to classify interstellar objects according to how many unusual characteristics they display and whether conventional explanations remain sufficient. Under this proposed system, ordinary natural objects would occupy the lowest levels, while a confirmed piece of extraterrestrial technology would represent the highest category. Based on the available observations, Loeb argued that 3I ATLAS deserved a relatively elevated rating because several of its features remained difficult to explain using existing models alone. His assessment immediately sparked intense discussion throughout the astronomical community. Many researchers emphasized that unusual observations do not automatically imply artificial origin. Others argued that every possibility should remain open until enough evidence exists to rule competing explanations in or out. The debate became even more fascinating because of comparisons with another famous interstellar visitor, Oumuamua, whose unusual acceleration continues to generate scientific discussion years after its discovery. Whatever 3I ATLAS ultimately proves to be, one fact is undeniable. It has already become one of the most closely studied interstellar objects ever discovered, reminding us that the universe still holds surprises capable of challenging our understanding of how cosmic objects form, evolve, and travel across the immense distances between the stars. As global interest in 3I ATLAS reached its highest point, the object suddenly vanished from view. It wasn't destroyed or lost. Instead, it slipped behind the Sun from Earth's perspective during solar conjunction, making observations impossible for several weeks. For astronomers, it was an unavoidable pause. Every major observatory had to wait patiently for the object to emerge from the Sun's glare before observations could resume. During this period, researchers relied on computer simulations and previously collected data to predict what might happen next. Most models suggested that after reappearing, 3I ATLAS would continue along its expected path toward the outer regions of the solar system, passing relatively close to Jupiter's orbit. Although no collision was predicted, scientists recognized an exciting opportunity. Depending on its exact trajectory, spacecraft operating near Jupiter, including ESA's JUICE mission and NASA's Europa Clipper, could potentially observe the object or analyze any dust and gas released from it. Even limited measurements could reveal valuable clues about the composition of an interstellar visitor. Others speculated that the unusual features detected before conjunction might become even more apparent after the object returned to view. Weeks later, that long-awaited moment finally arrived. Observatories across Earth and in orbit turned their instruments toward the predicted position of 3I ATLAS. What they found immediately caught everyone's attention. Instead of fading after its closest approach to the Sun, the object appeared noticeably brighter than expected. Its reflectivity seemed to increase beyond what standard models had predicted, suggesting that changes had occurred on or around its surface during its solar encounter.